Hello again, everybody, and welcome to another Geo-Institute live stream. It is, of course, the summer of live, and you have stumbled into part of it. I don't even know how many live streams we have done or will have for the rest of the summer, so I won't pretend to try to give you a number. Just suffice it to say that it's a lot, and you can go find them on our YouTube channel and subscribe to future ones on Eventbrite. My name is Brad Keeler. I'm the director of the Geo-Institute, and we are thrilled to have you with us for part 2 of the Geopier live series today. If you don't know anything about the Geo-Institute, after you watch this fine presentation today, head over to geoinstitute.org, and there you're going to find out a ton about us. Here are the important things. We're a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And when you go there, one very important thing I have on my person today, the Geo-Congress 2023 winning design for the Geo shirt. If you would like to show your support for our students, here is how you do it. I'm going to walk you through it. It's quick, it's easy, except that I clicked away from the web page, and so I'm going to bring it up really quick for you so you can see what you do. When you go to geoinstitute.org, you want to click on that top right part of the screen where it says Student Participation Fund. When you do that, you'll come to this lovely ASCE Foundation webpage. You can make your contribution to student programs here and get an amazing thank you gift, including your very own Ralph Peck bobblehead while those last. You want to have that on the shelf behind you as you join Teams or Zoom meetings. Show off to people your support for the Geo-Institute and your love for the great Ralph Peck. Important thing. We called this the Geopier Live series for one big reason. They sponsored it. So we have a message from our sponsors, Geopier, today. We're going to play that for you now, and we'll see you on the other side in just a few seconds. Thanks again to Geopier for their generous support of this live series. One more important thing that we want to thank Geopier for is their continued support for our Cross USA lecture series. Kyle, who's here with us today, was our Cross USA lecturer for 2023-2024, traveled this land doing many great presentations and did a few on our YouTube channel as well. You might recognize him from that. We did announce recently that our Cross USA lecturer for 25-26 will be Carlos Santamarina from Georgia Tech. Be looking for him at a chapter near you soon. And yes, we will have live streams with Carlos next summer on the YouTube channel. And that series is presented by Geopier as well. So with all that propaganda out of the way, now we get to the big show. And here to introduce Kyle, and he's going to ask some questions too later on, is you got to tell everybody what your title is, Aaron, because you've got a new one. He's an administrator at Minnesota State University, Mankato. He and I like to talk college hockey a lot. It is noted Deep Foundations guy, Aaron Budge. Aaron, thanks for doing this today.
Happy to do it, Brad. Happy to do it. Yeah, I'm the interim associate executive director of our School of Applied Agriculture for a certain stint anyway. But my heart is always in the civil engineering and geotechnical engineering realm. So it's definitely my honor today to introduce Kyle Rollins. Kyle received his bachelor's degree from Brigham Young University and his Ph.D. in civil engineering from the University of California at Berkeley. After working as a geotechnical consultant, he joined the civil engineering faculty at BYU in 1987, following after his father, who was previously a geotechnical professor. On a personal note, my Uncle Don, that Kyle would remember, served on the faculty at BYU with both Kyle and his father, Ralph, and always spoke very highly of each Dr. Rollins. So I appreciate having known of each of them for a number of years. I've known Kyle myself personally since working on my own graduate research project in conjunction with the Utah Department of Transportation and the I-15 reconstruction project in Salt Lake City just prior to the 2002 Winter Olympics. Kyle himself led a number of critical projects during that massive project. His research has involved geotechnical earthquake engineering, deep foundation behavior, bridge abutments, collapsible soils, and soil improvement techniques. He's published several hundred technical papers and supervised hundreds of graduate students. He was recognized as the Engineering Educator of the Year by the Utah State Engineers Council and received a Governor's Award for Science and Technology in 2017. ASCE has recognized his work with the Huber Research Award, the Wellington Prize, and the Wallace Hayward Baker Award. In 2009, he was the Cross-Canada Geotechnical Lecturer for the Canadian Geotechnical Society. And in 2013, he received the Jorj Osterberg Award for Innovation in Foundation Testing from the Deep Foundation Institute. More recently, he was recognized by ASCE with the 2024 H. Bolton Seed Medal, and as mentioned, was a Cross-USA Lecture Tour speaker in 2023-2024. With that, it is my pleasure and privilege to introduce Dr. Kyle Rollins. Kyle.
Thanks, Aaron. Let me see if I can get this sharing going. You seeing that okay?
You nailed it. We got it.
Hope so. Okay, well, it's a privilege to be with you today. I appreciate you sharing your time with us, and I hope I can make this worthwhile for you. We're going to be talking today about our experiences with rammed aggregate piers for liquefaction mitigation. We're going to talk about case histories from blast-induced liquefaction tests and actual earthquake tests. Appreciate the support we've received from Geopier and others in the ground improvement industry. If we're talking about methods for densifying soils, there are a variety of techniques that you could use: vibrocompaction, stone columns, dynamic compaction, compaction grouting. Today we're going to be focusing on rammed aggregate piers. And I don't have anything against any of these other approaches. They're all valuable, and every method has its pluses and minuses. But today I've been asked to talk about rammed aggregate piers, so we'll focus on that. Rammed aggregate piers use a mandrel that is driven into the ground surface to the depths that you want to treat, and then gravel aggregate is put into the pipe, the mandrel. Then it's raised maybe 3-4 feet, and then it has a compacting surface at the base that compacts the soil downward maybe 2 or 3 feet. So you have a lift that's compacted by impact and vibration. And the idea is that this is going to create a compacted column of coarse aggregate, maybe half an inch D50 size. And it goes down through this mandrel and through the hopper at the top. There are a number of mechanisms that might contribute to reducing the potential for liquefaction, and they include densification by the impact compactor and vibration that produces. Secondly, less well understood is the increase in the at-rest earth pressure coefficient, K0, from the compaction process, because you're expanding the zone, compacting it into the side of the existing soil. That's likely to increase the horizontal pressure. And then there's a third effect that's even less understood, but we are seeing it more often. It's the stiffening or reinforcing effect because of the interaction with the piers and the surrounding soil. So looking at the RAP installation objectives, we're going to try and increase the density. So if we have a sand with a blow count or a cone resistance of 75, and we can get it up to 150, it's obvious that if you're looking at liquefaction resistance, you could boost your cyclic resistance ratio substantially, as you see here, relative to that triggering curve. But there are also some issues with the at-rest earth pressure. We know when we compact soils with the rammed aggregate pier approach, we increase the K0 value. And the idea here would be that if we increase the horizontal earth pressure, we could also increase the cyclic resistance ratio due to that increase in K0. Not always, seldom considered, but an important event. And I'll explain this a bit why. What is the effect of K0 in liquefaction resistance? So Ishihara and others have found that as the K0 value goes up, the liquefaction resistance ratio, cyclic resistance ratio, goes up as well. That's been well documented because you're increasing the mean effective stress. There's just very little question about that. But on the other side, Salgado and others in a paper in 1977 pointed out that as the K0 value goes up, the CPT cone resistance is also affected by that K0, and to get it to the correct value, you need to lower it. So I'm showing in these two plots below that, can you see that horizontal red line with the red triangles? This is the adjustment factor to lower the CPT resistance to account for effects of that K0. And what they showed in their paper was that the net result was that there was no net improvement in the cyclic resistance ratio, the CRR, as K0 increased. Now that was back in 1997, and there's been a lot of additional work carried out. And you can see these curves in blue and black and green from Yamalkowski, a famous engineer in Italy, Boulanger in the United States, and Harada in Japan. And you can see that they're all showing higher factors, so saying that there's not as much as a reduction as you had thought. And some recent calibration chamber tests are shown with these red squares, and all these results are saying that you could have higher, you don't have to reduce that effect on the CPT as much as we thought. So in a recent study, we took all the data and used, we used this curve by Yamalkowski. It's not the most liberal, but it's kind of conservative and top end. And when we put that into the equations, we see that we do see an increase in cyclic resistance ratio with increases in K0. So as we're increasing the lateral stress from this and other methods, we could use these curves that are published in the ASCE Journal of Geotechnical and Geoenvironmental Engineering paper journal in June 2024. So this gives us a logical basis for including those effects. One of the problems of using considering K0 is that we have to estimate what it really is, and this is not as easy as we'd like it to be. There's equations that are proposed based on CPT and the dilatometer K sub D, but the best equations appear to be when you combine the effects from both the dilatometer K sub D value and the density from the Q sub C. And when both of those are used together, you get the best estimation of K0. Hossein and Andrus Clemson did a similar thing using both DMT values and cone resistance QC values to estimate K0. But again, that uses both CPT and DMT data, which would require you to do both tests. So we, as we do our research, we have this philosophy that one good test is worth 1,000 extra opinions. This is said by Wernher von Braun, who was the designer of the Saturn V moon rocket. And this wasn't because we're down on experts. You know, we all want to be experts. That's why we listen to things like this and attend ASCE, Geo-Institute congresses and so forth. But it means that we have to understand how the world really works. And once we do that, we can tailor our models and approaches so that they match real world behavior. I like to point out also that we have to have a healthy skepticism for tests. Einstein is reported to have said a theory is something that nobody believes except the person who proposed it. And an experiment or a test is something that everybody believes except the person who performed it. So we all know when we're doing a test that there are a lot of complications, and you almost never get a test that's perfect to where you have complete confidence. So you have to be a little skeptical and think through if this test is really what you think. So one of the first opportunities I had where we were looking at liquefaction mitigation with rammed aggregate piers was after the Christchurch earthquake sequence, where they had 3 or 4 earthquakes that caused significant damage. Out of 140,000 properties, 51,000 were damaged by liquefaction problems and settlement and ejecta and so forth and lateral spreading. That resulted in over $40 billion of economic damage to this small islands in South Pacific, and 33% of the financial loss was directly attributable to liquefaction in these red zone areas. So I was part of a team that was looking at the most cost-effective means for mitigating liquefaction damage for low-rise structures so that they could be authorized for use in reconstruction efforts. In the 2010-2011 earthquake sequence in Christchurch, very little deformation that caused damage in areas with liquefiable soils overlain by an intact, relatively stiff, non-liquefying crust with a thickness more than, say, 10 to 12 feet. So what the series of tests that were commissioned by the New Zealand Earthquake Commission said is, let's see if we can improve the top 4 meters of soil, allow the building to settle, but settle more uniformly maybe, even if the ground underneath it, maybe 6 to 10 meters, liquefies. So that's a kind of a brave strategy, but saying we can't really afford to improve all the ground, but maybe we'll make it so the deformation is acceptable. So as part of this $5 million study, they looked at 17 different strategies: rammed aggregate piers, low mobility grouts, soil cement rafts, resin injection, driving timber piles, and other approaches to try and create that 4-meter thick zone. And the idea is the thicker the zone and the stiffer it is, the better it ought to perform. So one of the methods was the rammed aggregate pier approach, and we looked at the CPT values before and after treatment. In the finer grain soils, there wasn't much densification, but as it transitioned to the coarser grain materials, we saw a significant increase in the cone resistance due to the treatment. And then it even densified below the base of the wrap, which was impressive to all of us looking at this data. In addition, we found out if we did shear wave velocities across the Geopier and in between the Geopier, we were seeing significant increases. It wasn't as much in the matrix soil. It was maybe increasing by 10%, but there's a 25% increase in the shear wave velocity as you go across the pier and back into the native soils. Now that has a big effect on the shear modulus, and that should affect what's going on. But it's hard to know how this really factors in to the performance. So to deal with, to see how all these factors, increases in density and K0 and shear modulus, were affecting things, we did a series of blast-induced liquefactions. There were 7 tests, 17 ground improvements, some houses we tested, manholes and pipes, and 3 fully instrumented continuous flight auger piles. And my job was to measure the excess pore pressures and the settlement and come up with the blast charge that we were going to use. So when I first heard about blast-induced liquefaction, my mind went back to this movie, Butch Cassidy and the Sundance Kid.
Well, that ought to do it.
We were trying to get enough explosives to blow up the safe, and that's what you just saw.
Think you used enough dynamite there, Butch?
So that's what that's what I first thought about this, a pretty crazy thing. When we showed up for our first job on Treasure Island, the blaster shook my hand and said, "Hi, I'm Butch." Then I got really nervous, but things turned out all right. And over the last, 20 years or so, we've done liquefaction tests all over the world, investigating performance of piles and ground improvement strategies. And that's what we used in Christchurch. So here I'll show you some tests. We're doing an unimproved site in the middle and improved method, ground improvement strategies all around here, and a continuous flight auger test down there, and to see how they would perform. So we're liquefying down to about 10 meters below the improved ground. So that was about 230 pounds of explosives detonating in over a 10-second period to boost excess pore pressure ratios. And we were very successful with that. Now, this was the plot that we used to see how well we were doing with the different ground improvement strategies. There's all of these plotted here where you're showing differential settlement on the vertical axis and total settlement on the x-axis. The greatest crust stiffness in terms of thickness and elastic modulus, say, are with the biggest circles. And you wanted to have the smallest amount of total settlement along with the lowest differential settlement. So as you look at these different strategies, you'll notice that rammed aggregate pier 1 is down here with high crust stiffness. Number 2 is down here with some of the lowest differential settlements, and rammed aggregate 3, pier 3, is here at probably the very best performance. So that was encouraging, seeing that the rammed aggregate piers might be effective in reducing the potential for liquefaction-induced settlements. But if you've got a keen eye, you'll also notice up here that there's rammed aggregate pier 4 that didn't work so well. It has some of the higher differential settlements and higher total settlements. So we're scratching our heads trying to figure out what was going on with this. It's so out of place. And then we talked to some people and said, that was the last pier that they were asked to do, and it was on the last day of the project that they were slated to be there. And you know what? We think because they were anxious to get out of there and get back home, that they may not have improved it as effectively as they did with the projects at the beginning. So this is kind of like buying a car on Tuesday after a long holiday. It might not be a good idea, and points out the need for investigation to make sure that the quality control is up to snuff. Okay, the second thing we're going to look at is an earthquake in Ecuador. It was a magnitude 7.8 earthquake in 2016, and I happened to be on the gear reconnaissance team that went down to investigate what had happened there. And this image shows the epicenter, and we're going to look at 2 case histories. You always want to see if that you can find 2 case histories with contrasting performance, so you can see what is causing the different effects to occur. So we're going to look at Boca de Briceño Bridge and the Mejia Bridge. Both have kind of similar peak ground accelerations, but completely different performance. So this is the Mejia Bridge. We went to this early on, and it was really amazing for us to see the failure. It's slumped down. There were cars had fallen into these grabens here, and the soil had moved outward, maybe 5 meters. A real kind of a circular failure, and that caused lateral spreading in the liquefiable soil below it. Now the layering here was interbedded sands and silty sands and some clay layers, even some gravel layers. But there was really terrible performance of this bridge. Then some people told us, hey, you need to go up to Boca de Brasino because it has had ground improvement and it's completely different. So we went up there and we were actually quite amazed in the team. It's even closer to the epicenter, a little higher acceleration, but very similar ground conditions, interbedded silty sands with some gravel. Can you see that pavement? There was an approach fill, had been treated with rammed aggregate piers, and there was very little deformation. You can see where that car's parked, that there was some movement back and forth that had some damage to the pavement, but it could be easily repaired. And we were able to travel over the approach fill and see everything in good shape. This is looking at the Boca de Brasino embankment. It's 700 meter zone of for the approach fill, and then a 70-meter bridge. And it was easy to find, going off the road a little bit, is easy to find lots of examples of liquefaction taking place with the characteristic sand boils all over the ground outside the treated area. But as we came up to the improved zone, very little movement of the abutments and very little damage to the roadway. We went back to the plans, and this was Geopier had installed these impact compaction piers. They're 20 inches and 20 centimeters. Let me get that right. 20 inches in diameter, so about 2 feet in place. Then they were spaced at 8. They went and treated 8 to 16 feet below the approach fill, and they're spaced 6.5 to 9 feet on centers. As they went back to less critical areas, they increased the spacing and went through the same process of improvement that we've talked about already. So some of my partners, Sarah Amoroso is an expert in DMT, and Brady Cox, an expert with shear wave velocity, went down to the site and did a lot of measurements in the untreated ground and in the treated ground underneath the embankment. And so that liquefied layer is shown in yellow outside the embankment, and inside you can see that interbedded nature up at the top. It's sandy silt. And then you have sand and silty sand layers. And then the rammed aggregate piers are supporting the embankment and densifying it. So I know this was, you don't like looking at tables, so I've just color-coded a little bit. So these are showing LPI values, which is a measure of the liquefaction and the intensity and thickness of that layer. So green values show low LPI values with low potential and low thicknesses of liquefaction. Red are very high, then moderate is yellow, and high is orange. So let's look at the free field away from the treated zone. You can see from the DMT, the Q sub C DMT correlations, the CPT correlations, and the shear wave velocity correlations all say there's a high potential for liquefaction problems. Let's go down to the slope and the top of the embankment. And a lot of those methods are showing green, or sometimes occasionally on the low end of the moderate range, right? That's underneath the embankment. let's go to another cross section. Here again, outside the treated area, everything's high potential for liquefaction. And then when we go to the same cross section, most of the zones from different improvement estimations, DMT, CPT, and shear wave velocity show that we've reduced the potential for liquefaction to a low level. Another approach to this was like, say, could we go in and maybe estimate what might have happened if we used like a pseudostatic analysis that considered the peak ground acceleration that's going on? And so this was done by Smith and Wisman and reported in the what was it? The meeting on soil dynamics and earthquake engineering in 2018. And if they just used the CPT and results that were obtained from these investigations, they have a factor of safety of less than 1, indicating that there would be slope failure. And this is the case. It's similar kind of rotational failure that we saw at Mejia Bridge and with all that lateral movement. Now, if you increase the resistance to consider the improvement provided by the rammed aggregate pier in installation, just considering only the densification, the factor of safety goes up to 1.08. My dad wouldn't have been too excited about that. He would say, we need to do something more. But that's what the factor of safety is. If you just consider the densification, if you consider densification and the wrap shear strength, considering only the portion that's actually being replaced here, the factor of safety increases to 1.2, where you could suspect that the pore pressures would be reduced enough to have pretty good performance. And that was actually the case. So that modifies, or that agrees with what we saw in the field performance. So that's a pretty good indicator that you might want to use that reinforcement strength in the rammed aggregate piers to get agreement with field behavior. The last one we'll look at is a test we did that involves soils with high fines content and how that we can improve them. Showing this plot by gradation plot by Mitchell, one of my professors at Berkeley. And it shows this blue range, which is the most desirable for ground improvement with low fines contents, less than 5 to 10%, is what you want to do to have the greatest potential for ground improvement success. But oftentimes we have cases which are outside of these ranges, and then we're left to think, what can we do? Which sometimes leads to soil mixing and very expensive efforts. Mitchell pointed out that the fines tend to reduce the permeability, making it less likely to be improved during vibration compaction treatments. And the fines tend to strengthen the soil structure as well. So what can we do? We wanted to investigate the effectiveness of rammed aggregate piers at sites with higher fines contents. And so we went to a site where they'd let us do the blast testing. It's in northern Italy, in a city called Mondeno. It's near Bologna, or Ferrara, where they make Ferraris. So we did see the museum while we're there, but you can see this aerial photo of the track rig that is inserting the Geopiers. Here's the forklift here dropping in the aggregate. This was again about a 12.5 millimeter diameter, half-inch D50 size. One of the things that was important here we found is this working platform. We were on soft ground, and the working platform wasn't the best, and we started tipping on when we got to the edge. So I know DFI has a manual out for working platforms, and from my little experience, I'd suggest you pay attention to that. So what we did here at this site is we put in 16, Geopier affiliates, SRL out of Mondano, did this installation of 16 Geopiers in a 4x4 arrangement. They're 0.5 meter diameter, so that's about 24 inches, and they're 2 meters on center, and they're extending to 9.5 meters into the ground, which was the zone that was, we thought most of the potential for liquefaction was. And we have those shown in blue dots. We monitored the pore pressure. We monitored the settlement in each of those rings. We had one zone that we'll call the natural panel that's over here, where we didn't do any treatment at all. And then we had another where we improved the ground with these rammed aggregate piers. And these red circles are where we detonated explosive charges. We detonated, and the sequence you see here, 1, 2, 3, 4, 5, 6, 7, 8. So trying to get movement going across the site. This shows the site characterization prior to treatment. We had a clay layer, Holocene material with low Q sub T. Then we get into a silty sand. It's also a silty, it's SM material, Holocene. And then we get into a silty sand, sandy silt, late Pleistocene, less likely to liquefy. The average in the improved area in the natural panel was very similar Q sub T values. The average I sub C in the zone we're treating is 1.6. There's correlations that predict the fines content. You can see they're not doing a very good job. They're estimating that the fines content was only 5%. In reality, it was something between 20 and 40% based on SPT sampling. The K-naught is pretty high, and it was about the same in both areas, the natural panel and the improved panel. And the shear wave velocity was similar in both panels. So we knew we had comparison apples to apples. As we started the test, we put in a lot of survey stakes across here to monitor the settlement of the ground. We also put in pore pressure transducers to monitor the water pressure. And we monitored the settlement also with drones, aerial drones, to see what was going on. Again, columns 0.5 meter in diameter, spaced at 2 meters center to center, which is a 5% area replacement ratio. Not very large. This plot shows the improvement that takes place, and the zone we are treating is shown with the dashed red lines. You can see the Q sub T value has gone up, not as much in areas where it's siltier, but a 30% increase. The I sub C value didn't change very much from after improvement. If we look at relative density using Kohlhaawe's equation, we get a 13% increase. Maybe not very big, but still substantial for the soil conditions we were working in. We also see that we're increasing the K-naught post-treatment. There with the red is post-treatment, the black is initial. So 30 to 100% higher in K-naught. And lastly, the factor of safety against liquefaction in the treated zone was about average of 0.87 before. And this area did show sand boils and fissures where ejecta came to the surface. So it was subjected to an earthquake in 2012 and did liquefy. After the improvement, the factor of safety was 1.28. So this was sufficient for their standards to say this was a successful improvement site. But we wanted to see how it would behave if we liquefied it again. We put some weights on here as well. and we're going to monitor the settlement and the pore pressure that's taking place. Pore pressure transducers could take the blast pressures and still survive and give us accurate readings. We had Sondex pipes so that the surrounding soil could settle and we could monitor the settlement as a function of depth. So as this corrugated pipe goes down, as the soil settles, we can now see how much settlement has taken place versus depth. So here's a video of that blast. Had a big crowd out to watch. Pretty great dig I've got. Shortly after the blast, we started to see water and sand ejected coming to the surface. You may be able to spot that in the middle there. There's another blast of water coming out in the middle of the area. And then there's one outside the periphery, 5 meters away from the center of the treated area. There's the drones going up. So as the excess pore pressures are being relieved, they're carrying that sand. You can see how dirty it is coming to the ground surface. So it was kind of an jaw-dropping experience for everybody who was there, because the contrast between the natural panel and the improved panel was fairly dramatic. We could see all this sand and ejecta that had come to the surface in the untreated area. And in comparison, there was very little ejecta and water in the improved panel. And there was, as we'll see here in a minute, a lot more settlement as well. This was rather surprising to everyone. Particularly important is this ejecta, because in Christchurch, about 33% of the problem was attributed to ejecta and leading to settlement of structures. So the lack of ejecta was important here. Inside the untreated area in the natural panel, you can see these sand boils, sand volcanoes that are producing substantial volumes of material. The excess pore pressure is pretty high in the natural panel, getting up to 100%. In the improved panel, there are a couple that were high, but most of them are down in the 70% range. We had a 1 pound charge at 4 meters and a 4 pound charge at 6.5 meters. And where the explosive charge went off, we overdid it. Maybe our blast was like Butch and the Sundance Kid. Maybe we had too much there, but we've got excess pore pressures of 1 there. But in the remainder, most of the area, we're seeing values of 70% or so. Whereas in the natural panel, everything basically liquefied with an excess pore pressure ratio of 1. So what is happening here now is this shows a cross-section of the settlement that we measured at the site. So we're getting about 4 inches of settlement in the natural panel. It's symmetric. And then over on this this improved panel on the left side, the settlement is not symmetric. The average settlement is about 1.5 inches maybe, but on one side, it's maybe approaching 2 inches. So we were wondering what's going on there. Here's from the aerial drones. They're showing a fairly symmetric settlement of 8 centimeters or 10 centimeters in the natural panel and a lot less in the improved panel, except for these two spots on this top right here. You see those where there's some significant settlement. We looked back and thought of the construction process. they immediately started this company, this affiliate for Geopier. This was their first job in Italy, and they started immediately on our production piles. I understand that most jobs, they have a test pilot area where they make sure that everything is working right. And in those first 2 or 3 Geopiers, what we saw is that when they did a constrained or a sustained loading test, where they're putting the full weight and pressure of the equipment on it, we were getting a lot of settlement, 8 to 10, 12 inches. So the piers weren't being adequately compacted, and they went back to the drawing board and improved it, and they got better performance with less than an inch or so at the other piers. So we think that was just a flaw that probably wouldn't normally be there. Our friends at University of Torino came down and did electrical resistivity tests. And can you see on that side where they were just recently put into place before the blast test? There's diffusion here where they really haven't improved the Geopier as substantially as it was in the other zones. And one day after blast, there's a lot of smearing here that settlement is taking place, more that was taking place there. And then 2 months after blast, the piers are distinct again. So we think this was a sign that the piers weren't put together very well at that corner. Here again, pointing out the need for quality control and dealing with the problems when you see them. Here's the final proof in the pudding of the settlement versus depth profiles. The volumetric strain in the natural panel was 1.33%. In the improved panel, it was only 0.33%. So that's a 75 reduction of settlement in the treated zone, which was pretty good. I thought was actually very good. And the installation depth, a lot of settlement was still taking place. We probably didn't treat as deeply as we needed to. It's hard to know how far the blast is going to treat. We wanted to see, could we predict this or compute it in some reasonable way? We used Zhang, Robertson, and Brockman's 2004 approach. We need the factor of safety against liquefaction and the CPT. So we come up to a factor of safety from our QSIB C1 and CS and estimate the volumetric strain. Knowing that CPT, we also needed to get the factor of safety or the residual excess pore pressure ratio can be used to get the factor of safety. We knew the pore pressure, so we could estimate the factor of safety. And knowing the factor of safety in the Q sub S, we could compute the settlement that we would expect to take place. And that is shown with the dashed red and blue lines computed, and the natural panel measured values is shown by that jagged result from the Sondex pipe. For my money, that's a pretty remarkable agreement that we had here, and we were pretty satisfied with that. We said, okay, let's use that exact same approach and calculate what we'd get for the settlement in the improved panel. And when we did that, we found out that we were overestimating the settlement that actually took place relative to the measured value. We're 50% off. So that's considering the excellent agreement we had with Natural Panel, we were pretty discouraged. Thinking further about it, we said maybe what we need to do is consider the stiffening effect of the rammed aggregate piers so that we can convert these columns and the natural soil into a uniform composite material and compute the settlement using this equation down here. The settlement due to reconsolidation is equal to the reapplied pressure, which is equal to 1 minus the excess pore pressure ratio times the vertical effective stress that the soil is under before liquefaction. So we knew the excess pore pressure ratio we were expecting, and we could calculate that value. H is the total thickness of the liquefied layer, and the denominator here is the composite stiffness of the columns and the soil. So we took the modulus constrained modulus of the rammed aggregate pier times the zone or the fraction of the zone that was improved, we could get this value from a catalog of static load tests that Geopier had conducted on rammed aggregate piers over I think there are 20 tests or so over their range of testing period. And then we have the modulus of the liquefied soil times 1 minus the replacement ratio. And we got these modulus values of liquefied soil from the Zhang et al. Approach that we had used to get the settlement of the soil so well in the previous example. And when we put those two together, using a plus and minus 25% range here, we start to see agreement that's consistent with what was measured. So in order for us to get acceptable agreement, we needed to consider the stiffness and the reinforcing effect of the soil. So concluding and wrapping up here, the RAP treatment reduces the liquefaction hazard by 3 mechanisms. It improves the density, it increases the lateral earth pressure, which you can take into account with the curves we've produced in our paper in 2024 in the ASCE Geotechnical Journal in June. And then these reinforcing effects, which we saw both in terms of vertical settlement from volumetric strain in Italy, and the reinforcing effects we saw from the earthquake performance in Ecuador. So these effects are confirmed by the blast liquefaction test that we saw in New Zealand, 2013. It's confirmed by performance in the Ecuador earthquake in 2016 and by the blast-induced liquefaction tests we've done in Italy. So my message would be trust, but verify. And that means that just because you're putting piers in doesn't mean that they are all getting done well. So do the testing, the quality control to make sure things are done well. Pilot approach before the production is, which is kind of the standard procedure for Geopier, is a good approach to see that you're really getting improvement. Do the test with the dilatometer and CPT and see if you can account on increased K-naught values and so forth. Anyway, thanks very much for your kind attention. And if you have any questions, you can email them to me, or hopefully we can address some of them right now.
Perfect. Thanks, Kyle. And yes, as mentioned, please enter any questions that you've got in the chat box. I know we've got a great group watching real time here, so please send those along, and Brad will pass them along to me. While we're waiting for a few of those to come in, I do have a couple of questions, Kyle. First of all, the videos were awesome. It's fun that the technology worked and the videos were very clear and the audio worked well, so appreciate the videos. And the side-by-side comparisons were also very cool to see the projects that were, very much side-by-side, similar conditions with very different results. So thank you for that. You've obviously been a part of a number of different projects through the years. Thinking about some of the depth considerations, diameter considerations of the various rammed aggregate piers you've seen, is there any real consistency, or is it highly variable as far as how that has been for the different projects? You mentioned the kind of the 4 meter zone that they were trying to improve in New Zealand. Has there been any consistent measures as far as what that spacing, diameter, et cetera, looks like for the different projects, or is it pretty project specific?
I think it's largely project specific. Geopier, I know, has a set of case histories that they've accumulated over the years that tells them for a given blow count or cone resistance how much settlement they might expect to have, and the density that they would achieve with different spacings. So they use that in-house guidance to come up with their design. I know the Japanese engineers, if they're going to treat some layer of soil underneath a building, they say if the treatment depth is Z, that they would have it go beyond the perimeter of the building area by a distance Z over 2. So half the thickness of the treated volume outside the area of where they want to have the structure or the building, the oil tank or whatever.
Very good. Questions are starting to come in, but I'll have one more here. You mentioned a little bit about the QA/QC options as far as what during the course of the construction. What are the suggested best practices as far as that quality assurance, quality control that can give the best indication as to whether that pier is being installed to the level it should be?
Well, first off, you need to make sure you're getting the gradation of the material that you specified, and that it's not getting contaminated. Then Geopier has some specifications. I believe it's called a sustained load test, where you put the full load of all the equipment can put down, and you want to have that be less than some target value. I think an inch or something was the standard. So it's great to come in after the fact, but it's really nice to have something while you're doing the construction that tells you you're on the right track, so you don't have it all done and then say, no, it wasn't good enough.
Tougher to go back and fix it after the fact, for sure.
Yeah, it's a problem. So we've often thought in a test area that you could do a pilot program is always useful, where you can go in and get before and after CPT and dilatometer tests, shear wave velocity tests. Of course, this depends on the budget and the scope of the work that's involved. You can't always do all these things, but these are all very useful to calibrate your results so you can be a little more effective.
Perfect. So let's see, a question from CMT Linden. Does the diameter of the wrap make much difference?
Well, yeah, the diameter depends on is one of the values you use for getting the replacement ratio. And as that increases, it increases the replacement ratio. They're typically, there's not a great deal of variation there, rather than just changing the mandrel size, which is often fairly, in this 0.5 meter to 0.75 meter range, sometimes a meter. You can adjust the spacing to get the replacement ratio that you're after. In some of the silty sands with 30 or 40% fines in Utah, you have to go to pretty high replacement ratios with stone columns and other treatments to get the improvement. So this will be site specific, I think, depending on what kind of improvement you're getting.
Great. A couple similar questions from Fernando and Eric about drainage effects, the aggregate providing some drainage compared to the surrounding soil, so less buildup of pore pressures. Should we be considering any potential for increased drainage limiting development of access pore pressures? What is the overall drainage consideration during the process of your design?
Yeah, that's an added safety factor issue, I suppose. I don't think most people in the Geopier world consider the drainage necessarily directly. We've seen cases when we're seeing water come out of the stone columns, for example, and even with rammed aggregate piers, we've seen water come out of adjacent piers when we're installing the other. So there is this drainage effect that reduces the excess pore pressure. We haven't considered that drainage benefit in the projects we've used with rammed aggregate piers in the past, but I think it's an added safety factor on your project that may not be directly considered.
Would help your father to have a little less heartburn about it.
That's right.
Perfect. So from Tom, have you done any testing in Charleston, South Carolina area with regards to the suitability of wrap for liquefaction mitigation in the Charleston area? PGAs are high, sands are typically fine, which I hear can make it challenging to get enough densification to be effective. Have you done any work in Charleston area and or similar conditions?
I know we've done some work in in Charleston, and there's been improvement there. We've done some tests with earthquake drains over the years in that area as well, and saw effectiveness of drainage even in that particular case. A lot. We haven't done a nice rammed aggregate pier blast test. It'd be fun to do. Been trying to get back to Charleston to do tests there. We did a test where we looked at lateral loading on large drilled shafts. I think there's one more blast-induced liquefaction test in. Maybe we can get back there. A lot of it, I think, depends on the plasticity of the fines that were involved. The ones we've had success with have largely been non-plastic fines, but if you start getting much plasticity in it, it becomes quite difficult. I know in Charleston, when we did the lateral statnamic load testing, that there was a clayey sand layer that we couldn't improve very much. We didn't see much improvement when the piles were vibrated in the ground there. So I think it may largely be a function of plasticity that we need to account for separately. Happy to do another test. Let's do it.
Related to that, Tempe has a question: what is the highest fines content range in the sandy units which were improved? So what is kind of the upper end of the fines?
At our sites, it was 40% was the highest. So I guess that's a short answer.
Okay. Let's see. Joel asks a neat question. Any consideration of complementing the wrap with wick drains in the silty sand sites?
I think that has the potential for being beneficial if it can be spaced closely. It reduces the pore pressures that are building up during construction. We've not done this with rammed aggregate piers, but we have done it in connection with stone columns with Keller, or in the day was Hayward Baker, and we saw significant improvements by putting the drains in place, both in terms of the improvement right after construction and then improvement with time because of the drains being in place, side-by-side testing with drains and without. So this is something we haven't investigated with wraps, but we know is effective for stone columns.
Okay, nice. From Atlas Indy here, what factors make wraps desirable compared to other mitigation methods? What are some of those positive attributes that make it above and beyond a better option?
Well, the Geopier people, I would say, would argue that they're, by compacting rather than just relying on the vibratory treatment, gives them a higher density of the fill material, which could lead to greater reinforcing capability of the material. I'm sure there'll be some arguments about that. And then there is some well-documented cases where you've got significant increases in the K-naught value that goes quite some distance out from the treated zone. There could be this potential from other methods, but each one of them needs to document those. One nice thing about Geopier's system is that they do have a case history database that gives us an idea of what the stiffness of the completed piers would be from static load tests. I think other organizations might have something similar, but this was very useful to us in trying to calibrate with our field measurements. So maybe some of those factors, and cost is another issue that we haven't gotten into, and I'm sure there's differences there.
Okay, very good. Ali has some questions relative to some of the cone penetration and other investigation data. Some of the CPT data after improvement showed that QC is reduced and increased. Why? Do you have any idea there? And also, what test would you use after installation of the Geopier to verify the effectiveness of the pier, CPT, or dilatometer, or otherwise? So you mentioned some of the tests that were done from your group.
Yeah, we've had some cases where we've these are with some vibratory techniques where we've disturbed the structure of the soil, like from the treatment, and we didn't see a big increase with time. It's kind of sat there a long period. But generally, with the non-plastic fines, over a period of 2 weeks to a month, we'll generally see the improvement increase, and so I know you don't always have the time to wait to see the improvement occur, but that's one factor that we've seen happen, and it can be a substantial increase. We've sometimes had some different results with shear wave velocity. The CPT and dilatometer have been a little more consistent in giving us improvement. But soils are interesting things. That's why I don't think AI is going to replace us too quickly.
Understood and agreed.
There's a lot of room for local experience and practice.
All right, a couple final questions here. It looks like Joel asks, where can we get the paper that you mentioned at the end of the presentation where we could read about a little extra about the stiffening effect of wrap? So is that paper readily available to folks?
Yeah, so you can look that up. I should have looked to see exactly when the date was. I think it's like 2020, 2021, something like that. It's you can search under rammed aggregate pier pile group. I'm the lead author, and it's in the Journal of Geotechnical and Geoenvironmental Engineering. You know, it probably in that period describes in detail all the process that I showed quickly at the end of this presentation, that work we did in Italy.
And the last external question here from Upul, that maybe you're familiar with, maybe not. There was a stadium in New Zealand that suffered large settlements of 200 to 500 millimeters after improving the upper 10 meters using vibra replacement stone columns. Any thoughts on what happened there? And I don't know if you're familiar or not with that particular site or project.
No, I probably know enough to be dangerous about it, but I've heard that for whatever reason they may not have improved it as effectively as they needed to. Or gone as deep as they might have done if they had a larger budget. So I know they didn't go back to that, and they were a little disappointed by performance, but I'm not certain what the actual reason was for the problems there. Again, we trust all these methods. We think they're good, but they need to be validated that we got what we were expecting in the design process.
Perfect. I guess the only other question I have is, are you now driving a Ferrari after your visit to the Ferrari Museum on the Italy project? I'm guessing.
Unfortunately, I can't afford one, but I do have a Porsche. Porsche came. Nice. My brother's got a Ferrari, and he's taken me around. But I'm hearing from people that the Teslas have the more acceleration than a Ferrari or a Lamborghini. So maybe you guys with Teslas can enjoy that acceleration lift.
My brother-in-law actually got a pretty cushy position as a maintenance guy for a Tesla, and now he's back with Toyota. So I don't know. He ended up just telling people how to run the fancy monitors and everything else. So
yeah.
Well, I think that's probably it for the questions. So Brad,
All
I guess
right.
we'll throw it back to you to wrap things up.
This was fantastic. Thank you, Kyle. I knew we were going to get a good crowd. And I told you yesterday when we went through your presentation that I knew we were going to get some good videos too. That is one thing you can count on when you have a Kyle Rollins presentation, both on the serious side, but the blast liquefaction stuff is so fascinating and really fun to watch. But Butch Cassidy, Come on, everybody. Where else are you going to get that? And if you liked what you saw today and you're here at the end, so you probably did, of course, click like, subscribe, and get notifications. And yes, if you do those things, we let you know every time we post something to the YouTube channel. We want to thank everybody for watching us today, especially those who ask questions. That's what makes these presentations so great, so vibrant. There's a great Q&A period at the end. You guys came through today. We really appreciate it. There were some great ones. Kyle's contact information is still up on the screen if you want to reach out to him afterwards with anything else that you might have about today's presentation. Our next live stream is 1 week from today. It'll be at 2 p.m. Eastern, just like we pretty much always do it. And it is our GeoStrata Extra episode 4, our August-September issue of the magazine. Georgette Halepis from the U.S. Army Corps of Engineers will be presenting about long-term dam monitoring. You do not want to miss that one. GeoStrata Extra is a lot of fun every time there's a new issue of the magazine out. And then, of course, next Thursday, we have our second episode of our new program, Hour of Scour, which, yes, as the name suggests, is about all things scour and erosion. Nina Stark from University of Florida will be our guest on that one. It's a little bit of a different format where we do things a little bit round robin. You might get me asking questions. You might have our host, Stacy Kaleza, asking questions. You might have Nina asking us questions. It's going to be a good time. You don't want to miss that. And you can register for all of our upcoming live streams on our Eventbrite page. Kyle, thanks again for an amazing presentation. Aaron, great job moderating. We really appreciate it. So everybody out there, enjoy the rest of your summer. We'll be at an Orioles game in a few hours, and then my kids are going back to school next week, and there's a lot happening. So enjoy what you have left out there in viewerland. Our producer today was Aurora Flieger, and we hope to see everybody soon with another Geo-Institute live stream.